Uber has grown into a massive data giant accumulating over 250 billion financial records, totaling up to over 300 terabytes in size. But the cost of storing these data on DynamoDB had skyrocketed. They needed a solution fast to stop losing $6 million annually. Uber uses Gulfstream, their platform to handle critical financial transactions that power their global operations. Given the financial nature, data integrity and auditability were the absolute priority. Under their hood, it uses LedgerStore, their custom storage solution that provided 4 key principles. Records are immutable once written, corrections are trackable, unauthorized changes are detected, and queries remain reproducible. LedgerStore acts as an abstraction layer, hiding the underlying database from the application. What's cool about this is that it lets Uber switch database without making any code change if they want to do so in the future. Their original database was on DynamoDB, which is Amazon's fully managed NoSQL database service that will automatically scale to handle any massive workload without requiring server management. It stores data as key value pairs and documents, making it flexible for applications that don't need rigid data structures like a traditional SQL database. LedgerStore uses an append-only ledger where you can only add data, never modify it or delete it, kinda like Bitcoin. When new data is inserted, the system checks if both the main table and all the indices can accept the write. Only when everything is ready does it actually commit everywhere simultaneously. This guarantees that the main table and all indices never fail out of sync. This is critical to prevent issues like double charging customers, losing money, or failing any regulatory audits. On top of that, they ensure that data doesn't get corrupted using 3 concepts. Sealing. This is like putting documents in a tamper-proof envelope. Once you seal a time period, nothing inside can be changed. The system creates a unique digital fingerprint. If anybody tries to modify the data later, you'll know immediately. Then there's a manifest, kind of like a detailed receipts. Each one lists exactly what's in the sealed time period, every record, what happened, and what digital fingerprint for proving that it's authentic. Then there's revisions. This handles mistakes after the sealing period. It creates a new layer saying, hey, when someone queries this record, show the corrected version instead. This enables corrections while maintaining a clear audit trail. This architecture would serve most companies, except this is Uber where millions of transactions are made each day. DynamoDB costs had become unsustainable at Uber scale. If you were to just take a look at the storage costs alone for something like DynamoDB's standard table for their 300 terabytes worth of data, we're talking about around $76,000 per month. And if you multiply that by 12, that's close to $1 million alone just for the storage. And this doesn't even include other things like read and write costs. The team needed a database that was cheaper, had 99.99 uptime, could scale horizontally, and streaming support. LedgerStore relies heavily on streaming data to build its manifest because reading from stream was much more cost efficient than actually scanning those massive tables. But switching database for a financial system, if that's not terrifying to you, then you probably think RM-RF is just spring cleaning. One mistake and it's over. So they really needed a bulletproof migration plan with the ability to instantly roll back. They broke the migration process into 2 phases. Re-architect core read and write operations for LedgerStore, which accounted for 75% of the storage footprint, and then handle system metadata and indexes later. After evaluating different options for databases, Uber said, this, I'll just do it myself, and decided to go with DocStore, their in-house distributed data built on top of MySQL that can store tens of petabytes of data and can serve tens of millions of requests per second. It consisted of 3 main layers: a stateless query engine that handles routing, sharding, and request processing, a stateful storage engine with MySQL backup using NVMe SSDs, which are capable of extreme heavy read and write workloads, and the control plane for managing the clusters. To handle high-scale read workloads, Uber built CacheFront, which is pretty much a Redis-based caching solution that sits in the query engine layer and uses change data capture for cache invalidation. This enabled them to serve over 40 million reads per second while reducing storage engine load by up to 95%. The next challenge was migrating all historical data from DynamoDB. They had two options. One, process everything into one massive Spark job. However, this approach had a major flaw because any error meant restarting the entire job from scratch. The second approach is to break the data into smaller subsets and migrate one subset at a time. This worked because ledger stores already organized data into ceiling windows. This parallel processing meant that you could scale the processing by just introducing more jobs. While Backfill handle historical data, they capture new transactions in real time using shadow writes, which would asynchronously insert live data into Dockstore alongside the primary DynamoDB writes. Since async writes could succeed on the primary but fail on the secondary, they implemented a two-phase commit protocol, ensuring both databases succeed or fail together, with a timer-based spot repair job for syncing any missing entries. To handle remaining inconsistencies, they added dual read and merge, concurrently reading from both databases, merging results and returning combined data. Once validation was completed and all data are in sync, they promoted Dockstore to be the primary and gradually reduced DynamoDB traffic until Dockstore was able to handle everything, while keeping a shadow write back to DynamoDB running just in case. After the migration, things were almost perfect except for one thing. You see, as data grows, one server will eventually run out of space. To solve this, data is typically spread across multiple partitions to handle the scale. This is where the hot partition problem comes in. This happens when most activity happens on one particular or a subset of partition while others just sit idle. In Uber's case, this can happen because millions of transactions happen at the same time. Imagine 1 million people booking a trip simultaneously after work because new episode of All the Wiring Whale, the Chinese Pokemon, just came out. All these ledger entries would have nearly identical timestamp. If you partition by course time, say second or minutes, all the writes can hit the same server, causing throttling and delays. When they were still on DynamoDB, they were able to solve this using dual table system. The buffer table uses hash function to distribute writes evenly, avoiding hotspots, while background jobs move data to permanent tables organized by time for efficient reads. When they moved to Dockstore, this issue was solved through its MySQL-based architecture. Dockstore uses a single table with a simpler architecture. It creates a predetermined number of data buckets that never changes, and as data grows, these buckets would distribute across more MySQL servers. The data timestamp is even more granular to prevent hotspot by creating many partition keys. It's interesting to see how much money they actually managed to save, but I do wonder how much it cost them to build such database and how much it actually costs to maintain and keep this database operational. Hey, if you made it this far, thank you so much for watching. I would really appreciate it if you can help this channel grow by hitting the subscribe button, like, and comment below. As always, thank you so much for watching and see you in the next one.